Every image in this video is real. No artist's rendering, no simulation, no AI-generated concept art. Every single frame you're about to see was captured by an actual camera on an actual spacecraft pointed at an actual place in our solar system. Some of these images took decades to become possible. Some were only captured because one scientist insisted on it against practical objections. And at least one of them was taken specifically so a book could open with the words, "Look again at that dot." Space imagery, more than almost any other kind of scientific data, has a unique power to make abstract facts feel immediate and real. A number describing Pluto's distance from the Sun is easy to read past without much feeling. An actual photograph of its heart-shaped plane, taken after a 9.5-year journey across the solar system, tends to stay with people in a different way entirely. That's part of why this specific list exists, not just to catalog impressive numbers, but to walk through exactly how each of these images came to exist, and why the story behind the shutter click is so often just as remarkable as what ended up in the frame. This is a tour through 10 of the most significant, most carefully documented images NASA and its partner space agencies have ever captured, where each one was taken, what it actually shows, and why, in every single case, the story behind the photograph is at least as remarkable as the photograph itself. On February 14, 1990, NASA's Voyager 1 spacecraft, already more than 7 billion miles from the Sun and long past its primary mission to Jupiter and Saturn, turned its camera around and looked back. At the specific urging of astronomer Carl Sagan, who had been part of Voyager's imaging team, the spacecraft captured a series of 60 images forming the first ever family portrait of the solar system, photographing Neptune, Uranus, Saturn, Jupiter, Venus, and Earth, all from a single vantage point far beyond any human's ordinary perspective. Earth appears in that image as a single pixel, roughly 1/10 of a pixel across, a barely visible mote suspended within a scattered band of sunlight, an artifact caused by sunlight bouncing around inside Voyager's camera optics. Not a deliberate spotlight, though the effect gave the image its unmistakable, almost theatrical quality. 3 planets didn't make the final portrait at all. Mars was too dark and too close to the same scattered light interference. Mercury sat too near the sun's blinding glare, and Pluto, already tiny and dim, was simply too small and too far away for Voyager's camera to resolve at all. Sagan later gave the image its now famous name in his 1994 book, Pale Blue Dot, a vision of the human future in space, writing the passage that would come to define how an entire generation thought about this single photograph. Look again at that dot. That's here. That's home. That's us. In 2020, on the 30th anniversary of the original photograph, NASA reprocessed the image using modern digital techniques, producing a sharper, more detailed version while preserving the same essential composition: Earth, alone, a fraction of a single pixel, against the vast empty backdrop of interstellar distance. It's worth appreciating that this photograph almost didn't happen at all. By 1990, Voyager 1 had already completed its primary mission, and turning the spacecraft's camera around to look back toward the inner solar system wasn't a scientifically essential task. The image offered little in the way of new data about Earth that scientists didn't already have. Some engineers at the time reportedly questioned whether the maneuver was worth the risk and effort, given the spacecraft's limited remaining resources. Sagan pushed for it anyway, specifically because of the perspective he believed it would offer. Not scientific data in the traditional sense, but a genuinely new way of visually understanding humanity's actual place in the universe. That the image went on to become one of the most enduring and frequently referenced photographs in the history of space exploration says something about how right that instinct turned out to be. Years before that final look backward, Voyager 1 made a discovery at Jupiter that fundamentally rewrote what scientists understood about volcanic activity anywhere beyond Earth. Photography of Jupiter began in earnest in January 1979, and by March, Voyager 1's images of the giant planet's brightly banded atmosphere already exceeded the detail of anything ever captured from Earth-based telescopes. But the truly historic image came from one of Jupiter's 4 large moons, Io. Examining photographs. Voyager 1 had taken of Io's surface. Navigation engineer Linda Morabito noticed a strange umbrella-shaped plume rising from the moon's edge, silhouetted against the blackness of space. That plume turned out to be an active volcanic eruption, the first time humanity had ever directly observed volcanic activity occurring anywhere in the solar system besides Earth. It confirmed a specific prediction made just days before the flyby by a team of scientists who had calculated that the intense gravitational stress from Jupiter's pull, combined with the competing tug of neighboring moons, would generate enough internal heat within Io to make it geologically active. Few predictions in planetary science have ever been confirmed this quickly or this dramatically by an actual photograph. Not every historic image in this list comes from a planetary flyby. In 1995, the Hubble Space Telescope captured what would become one of the single most reproduced astronomical images in history. the pillars of creation, three towering columns of interstellar gas and dust within the Eagle Nebula, located roughly 6,500 light-years from Earth. The image showed dense, finger-like structures of gas silhouetted against a glowing backdrop, with new stars actively forming within the pillars themselves, their intense radiation slowly eroding the surrounding material away over time. Hubble revisited the same structure in 2014, using upgraded instruments to capture a sharper, wider, and more detailed version of the same scene, allowing astronomers to directly compare the two images across nearly 2 decades and study subtle changes in the nebula's structure over that time. More recently, the James Webb Space Telescope has photographed the same pillars of creation again, this time in infrared light, revealing young, still-forming stars hidden within the dust that Hubble's visible light instruments couldn't see through at all. Together, the three images, 1995, 2014, and Webb's infrared version, offer one of the clearest examples in modern astronomy of how returning to the same target with improving technology continues to reveal genuinely new detail, even in a structure already photographed extensively before. On July 19, 2013, NASA's Cassini spacecraft, in orbit around Saturn, captured an image that had never been attempted quite this way before, and one that came with an unusual condition attached. Ordinarily, pointing a spacecraft's sensitive cameras anywhere near the Sun risks serious damage to its optics. But on that specific day, Saturn itself passed directly between Cassini and the Sun, briefly blocking that blinding glare entirely and creating a rare, safe window during which the spacecraft's wide-angle camera could photograph Saturn's rings backlit from behind, without the usual risk. Mission planners used that same safe window to do something deliberately shared with the public in advance. They aimed a portion of the same imaging sequence toward a very specific point in the sky, roughly 900 million miles away, where Earth itself would appear. Unlike Voyager 1's pale blue dot, captured without any public knowledge in advance, Cassini's 2013 image marked the first time in history that people on Earth knew, ahead of time, that they were being photographed from the outer solar system. And many took part deliberately, waving at the sky at the appointed hour. In the resulting composite, Earth appears as a small, pale blue point near the edge of Saturn's rings, with the Moon barely visible as a fainter smudge beside it. It was only the third time in history Earth had ever been imaged from beyond the orbit of Saturn, following Voyager 1's original 1990 photograph and an earlier, less publicized Cassini image captured back in 2006. Also, during its long mission at Saturn, Cassini captured a discovery that reshaped an entire branch of astrobiology, towering plumes of water vapor and ice particles erupting from cracks near the south pole of Enceladus, one of Saturn's smaller icy moons. First detected in 2005, these plumes shoot material hundreds of kilometers above the moon's surface, some of it escaping Enceladus's gravity entirely and feeding directly into Saturn's faint, diffuse E-ring. Cassini's images and direct instrument readings gathered during multiple close flybys through the plumes themselves confirmed that this material originates from a genuine liquid water ocean hidden beneath Enceladus's icy shell, and later analysis revealed that ocean contains organic molecules and chemical energy sources potentially capable of supporting microbial life, making Enceladus one of the most closely watched targets in the ongoing search for habitable environments beyond Earth. The photographs themselves, backlit plumes rising in delicate feather-like jets against the blackness of space, remain some of the most visually striking images any spacecraft has ever captured of active geology occurring in real time, tens of millions of miles from home. Cassini's mission at Saturn eventually ended deliberately and on its own dramatic terms. Rather than risk an uncontrolled crash that might one day contaminate Enceladus or Saturn's other potentially habitable moons with residual Earth microbes still clinging to the spacecraft after 2 decades in space, mission planners steered Cassini directly into Saturn's atmosphere on September 15, 2017. In a final planned grand finale plunge. The spacecraft continued transmitting data for as long as physically possible during that final descent, sending back real, measured details about Saturn's upper atmosphere until the moment its signal finally cut out, turning even Cassini's own destruction into one final genuinely useful scientific observation. On July 14, 2015, NASA's New Horizons spacecraft completed the only close flyby of Pluto ever attempted, after a 9.5-year journey across more than 3 billion miles of space. The images it sent back overturned decades of assumptions about what a small, distant, icy world at the edge of the solar system should actually look like. Rather than a featureless, ancient, crater-covered ball of ice, New Horizons revealed a genuinely active, geologically diverse landscape. Towering water ice mountains rising several kilometers high, vast plains of frozen nitrogen ice, showing signs of ongoing internal churning, and, most famously, a massive, bright, heart-shaped region roughly 1,600 kilometers across, informally named Tombaugh Regio, after Pluto's original 1930 discoverer, Clyde Tombaugh. The The mission also revealed complex, multi-layered blue-tinted hazes extending far higher above Pluto's surface than any pre-flyby model had predicted, a detail that continues generating new scientific discoveries even a decade later, as more recent instruments like the James Webb Space Telescope have gone back to study that same haze in greater chemical detail. New Horizons captured its historic images during a single high-speed flyby, since Pluto's immense distance and the spacecraft's own trajectory made any kind of orbit around the dwarf planet physically impossible with the fuel and propulsion available. That meant the entire close-up photographic record humanity has of Pluto, every mountain, every plain, every haze layer visible in any image ever taken of the surface up close, was captured within a window of just a few hours during a single pass, with no opportunity for a second attempt if anything had gone wrong. Engineers didn't even receive full confirmation that the flyby itself had succeeded until many hours after it happened, since New Horizons was programmed to prioritize data collection over real-time communication during its closest approach, meaning the spacecraft was, by design, completely out of contact with Earth during the single most important moments of its entire 9.5-year journey. Since landing in Gale Crater in August 2012, NASA's Curiosity rover has sent back tens of thousands of images documenting Mars's surface in a level of geological detail no orbiting spacecraft could ever achieve. Its cameras have captured ancient dried lake beds, cross-bedded rock layers indicating flowing water billions of years ago, and, in 2013, direct chemical evidence within drilled rock samples confirming that Mars once hosted environments genuinely capable of supporting microbial life, had any existed. Curiosity's successor, Perseverance, landed in Jezero Crater in February 2021, targeting a site scientists identified from orbit as an ancient river delta, a location where flowing water once carried sediment into a standing lake, the kind of environment on Earth most likely to preserve traces of ancient microbial life if Mars ever hosted any. Perseverance's cameras have captured detailed images of that delta's layered rock formations, and the rover has been actively collecting and caching rock core samples, specifically intended for eventual return to Earth by a future joint NASA-ESA mission, where laboratories far more sophisticated than anything that can be sent to Mars itself will be able to search those samples for genuine biosignatures. Perseverance also carried along a small technology demonstration that produced its own historic image, the Ingenuity helicopter, a lightweight 4-pound drone designed to test whether powered, controlled flight was even possible in Mars's extremely thin atmosphere, roughly 1% the density of Earth's own. On April 19, 2021, Ingenuity completed the first ever powered, controlled flight on another planet, and Perseverance's own cameras captured the historic moment from the ground, showing the small helicopter lifting off the Martian surface in real time. Ingenuity went on to complete 72 total flights before its mission finally ended in January 2024, having flown more than 30 times farther than its original technology demonstration goals ever called for, an achievement that has since directly informed the design of future planned Mars aircraft. Since becoming operational in 2022, the James Webb Space Telescope has repeatedly turned its infrared instruments toward the planets of our own solar system, revealing details invisible to telescopes working only in visible light. In September 2022, Webb captured Neptune's rings in the clearest view achieved in more than 3 decades, since Voyager 2's brief 1989 flyby remains the only spacecraft ever to visit the planet directly. Webb's image revealed several of Neptune's fainter, dustier rings, along with a crisp view of several of its moons, all visible in a level of clarity ground-based telescopes, and even Hubble had never quite matched at these particular infrared wavelengths. That same year, Webb also turned toward Jupiter, capturing its enormous auroras glowing at the planet's poles, its faint ring system, and 2 of its smaller moons, all in a single infrared composite that revealed detail invisible to conventional visible light cameras. Webb has since observed Saturn as well, capturing its rings in exceptional clarity while revealing several of its moons as faint points against the darker infrared backdrop of the planet's atmosphere. Each of these images represents the same basic scientific value. Infrared light passes through atmospheric hazes and reveals compositional and structural details that visible light images, however sharp, simply can't capture on their own. Webb's ability to observe our own solar system's planets was, in some ways, a genuine engineering bonus rather than the telescope's original central purpose. Webb was primarily designed and funded to study extremely distant galaxies and exoplanets, objects so far away that their light has taken billions of years to reach us. Turning that same extraordinarily sensitive, precisely engineered instrument back toward much closer, much brighter targets within our own solar system required careful planning to avoid overwhelming its sensors, which are specifically optimized for extremely faint, distant light sources rather than comparatively bright nearby planets. That Webb has managed to do both, probing the deep, ancient universe and revisiting our own planetary neighbors in unprecedented infrared detail, reflects just how versatile its final design turned out to be, beyond even its original core mission requirements. NASA's Juno spacecraft, in orbit around Jupiter since July 2016, has produced some of the most artistically striking images ever taken of the solar system's largest planet, thanks to a highly elliptical orbit that periodically brings it extremely close to Jupiter's swirling cloud tops. Juno's JunoCam instrument, whose data processing was deliberately made public specifically so that citizen scientists and amateur image processors around the world could enhance and refine the raw images themselves, has produced now famous views of Jupiter's turbulent polar storms, arranged in striking geometric clusters unlike anything previously observed on the planet, along with detailed close-up looks at the Great Red Spot, a storm system that has been raging on Jupiter for at least the past 150 years and possibly considerably longer. Juno's images of Jupiter's poles specifically revealed something nobody had predicted before the spacecraft's arrival. Rather than a single, organized polar vortex the way Saturn's poles display, Jupiter's North Pole hosts a cluster of 8 enormous hurricane-like storms arranged in a near-perfect octagonal pattern around a 9th central storm, while its South Pole hosts a similar arrangement of 5 massive storms in a pentagonal formation, a genuinely bizarre, unpredicted structure that images alone, rather than any prior theoretical model, first revealed to scientists. What makes JunoCam's contribution genuinely unusual within NASA's broader history is the decision to make the instrument's raw image data freely available to the public almost immediately after each close pass, rather than reserving initial processing exclusively for professional mission scientists. That choice transformed JunoCam into something closer to a genuine collaborative project between NASA and a global community of image processing enthusiasts, many of whom have developed their own specialized techniques for enhancing color, contrast, and detail within the raw data, occasionally producing versions of Jupiter's clouds that circulate more widely online than the mission's own official released images. It's a genuinely unusual model for a major NASA planetary mission, and one that has directly contributed to the wide, enduring public fascination with Jupiter's turbulent, endlessly shifting cloud tops. Every image in this video represents an enormous, often multi-decade investment of engineering, funding, and scientific patience. Voyager 1's pale blue dot required a spacecraft to survive over a decade of travel before anyone could even attempt the shot. New Horizons' image of Pluto's heart required 9.5 years of transit before a single, irreplaceable flyby. Cassini's Saturn eclipse image required over 900 million miles of distance and a precisely timed alignment that occurs only rarely. None of these were lucky snapshots. Each one represents deliberate planning, genuine risk, and years, sometimes decades, of patient work before the shutter finally opened at exactly the right moment. These images also share something else in common. Each one changed how scientists, and often the general public, actually understood some part of the solar system. Io's volcanic plume rewrote assumptions about geological activity beyond Earth. Enceladus's ice plumes opened an entirely new category of habitability research. Pluto's heart-shaped plain revealed genuine, ongoing geological activity on a world many expected to be a frozen, inert relic. Jupiter's octagonal polar storms revealed a planetary weather pattern nobody had theoretically predicted before Juno's cameras actually captured it. In every case, the photograph itself became the evidence that reshaped the science, rather than simply illustrating something already known in advance. There's also something worth appreciating about how these images continue to be revisited, reprocessed, and re-examined decades after they were first captured. The pale blue dot was reprocessed with modern techniques for its 30th anniversary in 2020, 3 decades after the original 1990 exposure. Pluto's haze, first photographed by New Horizons in 2015, is still actively being studied using the James Webb Space Telescope's far more sensitive instruments a decade later. Even old, seemingly finished datasets keep yielding new scientific value as processing techniques and follow-up instruments continue to improve. A reminder that a single well-captured image can keep generating genuine scientific discovery for years, or even decades, after the shutter first closed. It's worth closing on just how differently these 10 images will likely be remembered decades from now. Some, like the pale blue dot, have already become cultural touchstones well beyond the scientific community, referenced in books, documentaries, and everyday conversation about humanity's place in the universe. Others, like Jupiter's octagonal polar storms or Enceladus's ice plumes, remain more specialized, primarily known within the scientific and space enthusiast communities, even though their underlying discoveries were genuinely significant. And a few, like Perseverance and Ingenuity's ongoing work on Mars, are still actively being written, with their most historically significant chapters likely still ahead, once sample return missions and future crewed exploration eventually build on the groundwork these current missions have already laid. If you want to see the next genuinely historic image NASA captures, whether it's the next flyby, the next JWST observation, or the next Mars rover discovery, Subscribe to the channel and turn on notifications, because when that image comes in, we'll break down exactly what it shows here with the real story behind it, not the invented version. 10 images, several decades of patient engineering, a solar system that keeps revealing more of itself, one carefully timed photograph at a time. Thanks for watching.